recording.
You're good. Thank you.
By the way, Jenny, all of my guys and kids are there. So it's good. For the summer folks.
Okay. For the July one?
Yeah. Okay. But Jenny said that she's fine. So it's good.
She's in the current one?
Yeah.
Okay.
But I told her it's not the feedback.
Yes.
Cool.
The assistant to the chair. Okay. Okay, crazy. And,
Morning.
okay. Yes. But yeah, you should. It's crazy. Good morning.
Good to see you back.
Yeah, that's what I felt like, two different finished, so I was like, okay, actually, that's awesome.
Good. So it's all, they all went well?
I mean, we're waiting to find out that waiting period.
Good.
Yeah.
Pretty good. Good.
Very low.
So if you use new channel one, orientation, sometime in August. I'm trying to remember, usually there's a VA.
Right.
In August, but I work with that department, so I'm playing with that. So I think it's going to be. Yeah, okay, so I think we've got something else right here, so I think we are, I think it's going to be the 25th. But until that time. We've got your.
That's what Dr. Estrada told me.
Okay.
Orientation.
And you're on the email list, get all the notices.
Well, I get someone from CCTS, but I don't get the one about this.
Okay, so like, did you get one about, okay. I will email Eve.
Okay,
Get you to get
I just got a welcome email to sign up through CCTS. I didn't get the email about this stuff.
Are you getting the emails from the
Yeah,
health policy of the service?
Yeah, after you emailed her.
Okay, perfect. I'll get you.
Great, thank you.
Sam.
Are you with the VA?
Yeah.
Oh.
2 years.
Oh, cool. I did medicine and health care.
Here.
All right. Good.
It's 1 year. Yeah, thank you.
Oh, yeah, I saw you have. He told me about you. Me too. Because I don't know the fine. And like,
Yeah, yeah.
and he is fantastic. So
It's pretty hard for me.
Yeah. She's had a never, yeah, I know, I don't know. I'll be honest with you. Is this something you want to know about? He's like, no, I'm like, great. I'll make sure it comes to money. He's like, yeah, that's something you know about. I didn't do any of all of my school, so I have no idea. I've been blessed before.
What's that? It doesn't matter.
Or bulldogs and stuff. I don't know.
Yeah.
Yeah. That would be expensive so much.
Yeah. Well, there's some training.
Yeah, she goes to that's good now. I'm my friends were doing that for even short time now. So they're 5 years. They think they're fellowship. They're like that.
Yeah, they figured it out. Yeah.
Yes, my friend is just having some friend out. And I'm like, I'm probably gonna
Yeah,
go.
you said it.
Oh, yeah.
Yeah.
Very nice to meet you.
I just got a message from Dr. Redden. He is walking now. Hopefully he's walking in this direction. Before he gets here, I'll just take a few moments. So, great to see everyone. I know we've got some new faces. It's kind of an interesting time because we're about halfway through the summer program for the CCTS, which is a partnership between UAB and Tulane, who's with us remotely. You can see them on the camera. So they're about halfway through. These are med students. They're between their first and second year. At the same time, we've got for our AHRQ funded T32 and the VA Quality Scholars, we've got new postdocs and pre-docs that are coming on board. They're just starting their 2-year appointments, and we've got some new folks for the TL1 program that will be joining us, and then we've got people from the year out TL1 ending. So it's just a nice combination of a variety of different things, but it's a good group. So I say all that to say, as we wait for David, or even after David wraps up today, take a moment to kind of introduce yourself, ask people around you what they're doing, you know, where they're at in their career, and kind of learn from each other for that. A few other housekeeping things. So we've got 3 more sessions coming up for the summer program. We've got team science, we've got community engagement, which Monica Baskin will do, and then we've got our wrap-up, which is the summer trainees presenting. And then in August, we've got Dr. Crossell-Wood is going to be giving a talk, and I'm blanking on the dates, but she's going to be giving a talk on mentoring, and then we'll be doing our orientation for our year-long TL1, the T32, and the other programs, which again are, we encourage all of you to apply. And by then we will also have identified who are new, both CCTS and PCOR K scholars, which are junior faculty. So a lot of new faces, so introduce yourselves and have time to interact. Any general questions, either here at UAB or at Tulane, that I can answer right now? So David should be here very soon.
This is the end of the stats.
This is the second one. So David gave the one earlier and wasn't able to, there was a lot of good discussion, so he wasn't able to get through everything he wanted to. So this is kind of stats 102. as we called it. But for those that don't have it, we do have the first session recorded. We're recording this one. David has been very happy to share his slides. Anything we can do, again, just even as if you want to share it with other folks or as a refresher for yourself or anything. And just as a reminder with that, the CCTS, through its BIRD, which is Biostats Epi Research Design, BERD, has weekly drop-in clinics both Monday at the Edge of Chaos, but also Wednesday here. Around lunchtime, they do provide food. It's open to everyone, doesn't matter your career level, doesn't matter who you're funded by. Always welcome to just drop in and get advice on what you're doing. And then there's also office hours. This is actually David's typical office hours on Fridays. There's other ones throughout the week that we'd be happy to share. And it's a simple thing of either just showing up or at any point you can email ccts@uab.edu. That's the CCTS email. And just say you've got a study design or a statistical question or whatever. We'd be happy to connect you with someone to help you answer those questions. And even if you've got someone, as I've said before, even if you've got someone that you're working with, your mentor works with, never hurts to get a second opinion, second set of eyes to kind of look at that.
And you can also email me. So I'm Emily Levitan. I'm also one of the BIRD, I'm an epidemiologist. So I can answer some stats questions and a lot of the study design questions.
I was just trying to be nice and not flood her email. But no, Emily is phenomenal to work with, and as you know, she presented earlier this summer on study design. And Emily is routinely, as long as she's in town, is routinely here on Fridays. And again, part of this gathering is for opportunities to have discussions afterwards. That's part of the reason why we host it here, is there's places to have little breakout sessions if you want to have ongoing discussions, walk over to Lucy's, what have you. So another way to connect that way. And Mike Mugavero, who should be here this morning, is another one that is routinely here. We've got faculty. So, but also use me as a resource. If there's anything I can do to connect you with resources on campus, let me know. Quick question I talked to Jenny earlier, for the summer trainings both here at UAB and also at Tulane, how is the Kaizen game going? Any glitches? Any issues? Is it fun?
We've been doing Kaizen for med school.
Yeah.
The last year.
Yeah.
I think we're just kind of used to having Kaizen questions all the time. So.
Is it much different than the ones that you were doing in med school? Is it about the same?
I'd say it's pretty similar. I mean, there's a set of material, and there's questions directly out of that set of material.
Are you guys tired of it yet? The reason I asked that is not to put you on the spot, but we're excited about it, partly because we haven't used it, but we're also trying to figure out what other aspects of training can we incorporate into a gamification approach so that it's not lecture, classroom.
I think gamification is great. I think gamification works best when people really want whatever the reward is.
Okay.
Does that make sense? Particularly gamification for things like information in terms of absorption.
So it's not the knowledge enough. It's the pizza party. It's the getting out of a test. It's
for games like that. I think that's my theory.
We were talking about gamification, and how it was going, and part of the feedback is it depends on the prize.
Okay, well, what do you want the prize to be?
Cash.
That's going to be kind of hard from the university rules. The prize I made for the Biostats honors class is if you were in the top 5%, you got out of the final. And they played.
This is it, right?
Update.
All right. I'll manage the chat. We do have Tulane and we've got Justin remotely. I'll manage that. So those that don't know, this is Dr. David Redden, who is the chair of the Biostats department, also leads the BIRD component that I was mentioning with the CCTS. He's a little hard to hear, so, but I'll hand it over to you.
I think I need a mic.
Yeah.
Okay, so there's going to be a little bit of refresher because, I will always argue that statistical power is probably the only reason they keep me on the campus, is to be able to help people write a calculation, to help people think about it in the correct way. But for those of you that heard the lecture a few weeks back, I told you, and I should have picked it up last night, really modern statistical theory is a combination of two very disjoint theories, set up by Fisher and the other one set up by Damon and Pearson. And what we've done is kind of smushed them together. And when you read the textbooks and you find yourself getting confused, the reason you're getting confused is because people came from very different philosophies, and we just kind of blended that in the modern textbooks. And so what we've kind of created is a spork. Half spoon, half fork, and it's not really that natural after all. But what I want to do here is to get you to think about, if you are designing something, it is your responsibility to say, if I am going to use a p-value to report whether I achieve statistical significance or not, if you're going to put a p-value down, I think you are going to be required to discuss what is your statistical power. And it's almost like, I hate to say it, some people, if you go about building it from the correct perspectives, it's really not that mystical. But I hate to say it, you really need to forget everything that they tried to teach you in the first stats course about power and throwing up all those formulas. There will be no formula put on the board today. There will only be graphs. I would rather look at graphs when I'm talking about power. So we're going to talk about what statistical power is and what it is not. Okay? I'm going to tell you the first thing that you need to be worried about when you're going after your power calculation, and you're going to be surprised that you think, I'm serious, everybody, a lot of people will stop me on the street and say, hey, can I discuss power with you really quick? I'm not joking, they will. And they'll start out, and my comment is, actually, we probably just should sit down and have a cup of coffee first so that I can understand what you're measuring. If you haven't decided what you're measuring, it's not time to talk to me yet. That's the key thing. You first have to decide what you're going to measure. Then the concepts that guide the calculation. I have redone this one. I actually was up early this morning. We got two group comparisons because that's pretty much a very common thing people come to me about. Then we come in about two group for proportions. That's another thing. If you get those two fundamental things down, you pretty much got 80% of the turf. Everything builds from there, but there's only one concept behind it. I do not care what statistical test your hypothesis forces me into. I do not care. The concept behind power is only one concept. And I want you to be able to understand, you have to say, what is occurring and what do I anticipate to occur if the null is true? Suppose I'm having no effect. How should the data behave? And then if a clinically, now notice I said something, clinically relevant effect exists. Don't care what statistically significant is. You have to be able to tell me what matters from a clinical perspective. If you can cover those first two, then you've got 80% of the turf. Then I'm going to go to the other one where it's ANOVA to show you, okay, it's now more complex, but it's the exact same game. It's the exact same game. And why the most important part of the power section is not the calculation. You will get all consumed about, give me the number. Let's get it down on a piece of paper. But the catch is, you can get the number right and still get triaged over the power calculation. So I want to talk to you about that also. All right? Here's David's layman explanation. See, I didn't even put any Greek in there. Okay? It's a description, folks. It's a description about possible experimental outcomes for which we are likely to declare the intervention or the experiment worked. Again, remember what I said a few weeks ago. Really, all I think about on a day-to-day basis is probability. And what a power calculation is very simple. If you have made a difference, a clinically relevant difference, it is the mathematical probability of declaring statistical significance. In other words, it's the chance that if, notice the condition, given the effect exists and my assumptions are correct, then what are my chances of declaring I found it? Folks, it's no different than me telling you that there's an 80% chance of rain today. Same concept. I'm just saying under these conditions, we believe that there is an 80% chance that it will rain. When I do a power calculation, under these conditions, I believe that there is an 80% chance you will achieve statistical significance. That's all it is. The other thing, so the first one is focusing on allowing me to come in and saying, David, you can do all the magic you want to, but I can't afford more than 90 people. Half my power calculations start that way. I had one that started yesterday. David, we're going to go for a grant next year. We've got 15 hospitals. What can you do? Okay. There's nothing wrong with that. So they told me the sample size. They told me what they're going to measure. We meet next week to say these are the possible effect sizes. The first one's a definition of effect size. What is detectable? The next one is the sample sizes. Some people will say, well, I need a power calculation. When 9 a.m. today, somebody's going to say, I'm going to need a sample size calculation. At 9:30, somebody's going to say, hey, I need a power calculation. Same thing. It's the same thing. Okay? It's just a matter of what endpoint am I solving for. Any formula I can invert, manipulate, solve for what you give me for, of 4 or 5 unknowns, I can figure out what the fifth one should be to make the equation work. Key thing, when you get ready to meet with a statistician or a methodologist, epidemiologist, whoever's helping you with the power calculation, you really need to think about, what am I measuring? Is it continuous? Is it yes, no? Or could it have more categories, but is it a categorical variable? That's the first thing I'm going to need to know. Okay? And then we have to have a discussion of what a meaningful effect is. That's not the end of it, but that's where it begins. What it is not. It is not the first thing to be worried about. Seriously. I get really amazed at, even after all these years, how many people will be so amped up about, the power, that they come to me and they're shocked that I take the whole conversation to, hey, let's talk about specific games. Can I please see the specific games? Can you educate me, please, with regard to what's the biology behind this mechanism? Can you tell me how this is being measured? Is it yes, no? Is it the time it takes to get this done? Do you really consider this a quantity, or do you consider this a quality? All of these things matter because it shapes, remember what I said, the specific aims lead to the hypotheses. Okay? Every time a statistician thinks about any experiment, we're going to think about hypotheses, null, alternative. Then, once we have those hypotheses, we know immediately what we're going to do with the analysis plan. And once I have the analysis plan, I know the method that maps to the power calculation. Do you see, I can't start at the bottom. I can't even start with the analysis plan. I have to go all the way back to the specific aims. So that's the first thing. Please understand it's not a guarantee of success. When I tell you you have 80% power, I can set up computer simulations and run it over and over. Do you know what? under that simulation, when I know for a fact that the effect is there, I programmed it. I'm making the computer do the mathematics. I do 100 experiments under the exact same conditions. If I say there's 80% power, I'm expecting 80% of the p-values to be below my 0.05 level. If I've set my type 1 error rate at 0.05, what I'm literally saying is I'm expecting 80 of them to be below 0.05 to say statistically significant. That means 20% of the time the real effect is there, and the method failed to detect it. Okay, so you got to keep in mind, and a little tidbit that I've learned over the years, when I first got into research, when I was first doing this, I always just went to the tried and true, because it's in the textbooks, right? It's in the textbooks. 80%, 80%, 80%. I don't do 80% anymore. No. The first thing I come in is I say, all right, let me talk about 85% power, 90% power. But David, you're costing us more. Yes, but I'm buying you insurance. I'm buying you insurance. That's what I'm doing, because by going up higher on the level, power curves are not linear. They have curves in them. They're trying to get you to a plateau that if some of my assumptions are wrong, you don't fall off a cliff. So the further up the power curve you can go, the better. Please understand, the first, you can always see, it's interesting because I think people recognize now, a lot of people will say, David wrote that power calculation, David wrote that stat section because I plagiarize myself all day long. But I also just have the same writing style. But you will always consistently see when I write a power calculation, the very first word is, assuming, I telegraph it, assuming the following pieces, then we can declare this. And so, gotta understand, it's a swag. You know what a swag is? Scientific, wild, I'll let you fill in the A, guess. Okay? If you need me to explain later, I will, not in front of the mic. But it's a swag, that's all it is. How to approach it. Don't go looking for a formula. Don't bother with that. First, don't go looking for power calculators on the internet immediately. Please don't. Be careful of those. A lot of them are wrong. A lot of them do not produce the correct values. If you do, I'm not saying you can't do your own power calculation. I'm saying please have someone double check it. I don't turn in a power calculation without asking Andy Westfall or someone else to read this to see if they can replicate it. Please, always start with your specific aims. Always. When you're coming to me, even if they're just rough, bring them. Because that's the very first place that we've got to begin. Think of how you will measure the outcomes. How much of it is, how big of it comes back to when MDs, a lot of times when I have these meetings, in the power when I was meeting yesterday on the design of a grant that's going to go next year, very senior researcher on this campus, you could just see when I said, what's a clinically relevant effect? Oh, they did not want to answer that question. Because they were uncomfortable. Because it's purely a scientific opinion. Well, what if I'm wrong? To which I glibly responded, oh, you are. But it's okay. It's a guess. Just give me an effect. And as a methodologist, I'm going to be wise enough to say, you come to me and say, okay, David, it matters that it's a 5-unit change in blood pressure. All right, that's fine. And you give me the standard deviation. Do you think I'm going to come back and just say, here's the one power calculation? Let's just assume 5. I'm going to come back and say, if for some reason you change your mind and you say, really, it could be 3, here's the other options. I'll give you the grid and we will sit down and discuss it so that you remember, the power calculation is trying to describe the landscape of the possible outcomes. So you would like to be able to give a table or a grid, I find the table and grid more informative than the curves. Some statisticians, methodologists would rather provide curves. I find the actual tables more useful. Then after you've done these three things, it's time to meet with the methodologist, but not before. I would argue this: if you were waffling on number 3, it's okay, come on. Number 1 and number 2 are sufficient, but don't walk into the meeting without anticipating that the conversation is going to immediately go to help me know what matters. And please keep it, and I cannot emphasize this enough. You've got to be able to say what clinically matters. People will confuse this all the time. Well, I want to find something that's statistically significant. Okay, I can give you a sample size of 10,000 and you will split the difference of a hair. Okay, and we've wasted resources, but you've got statistical power to get there to find something that is clinically irrelevant. That's a waste of resources. Okay? Then the other danger is you go with a sample size that's so small that you're really going to have to you better hope you're creating a Grand Canyon between the two groups for you to be able to declare statistical significance. So it's trying to balance those two edges and find the compromise. Okay, so let's go through it, all right? Keep in mind, power. We can discuss p-values or we can discuss rejection regions. I'm old enough and I've told everybody this, and this is the truth. I made it all the way through my undergraduate program, bachelor's in mathematics with an emphasis in computer science, with 4 courses in statistics, and do you know the one concept I was not taught? P-value. Graduated my undergraduate in 91. There was no discussion of p-value at that point. It was all rejection regions. Draw the curves. Put down the fences so that if you fall in these regions, you reject. If you do not fall in those regions, you do not reject. That was it. That's Neyman Pearson. That is classic Neyman Pearson. Because under those concepts, power becomes crystal clear. People get confused because p-values and power weren't designed together. Rejection regions and power were designed together. So, under the null hypothesis, okay? Null hypothesis is the one that we believe to be true until evidence is provided otherwise. Jury trial. Innocent until... All right, we're going to assume this. Scientific method assumes your experiment does not have an impact. Your therapy does not have an impact. Your intervention does not have an impact. Therefore, if I'm doing a 2-group test, I say mu1 is equal to mu2. It's just that easy. Then I believe that I have 2 distributions. I want to assume for right now that they are bell-shaped and that the 2 means line up right over each other. And if those means line up right over each other, then I will not declare, or I do not believe that there's a meaningful difference. Okay? Now, here's where it gets difficult for power. Now you have to start imagining. You have to start postulating, throwing out possibilities. What could be going on under the alternative? So, for example, if I assume mu1 is equal to 30 and mu2 is equal to 30, they're equal. That's a combination that maps into the null. Okay? Power for that's 0.05, folks. Probability I'm going to reject that when that's the truth, 0.05. You graph power calculations for a 2-tailed test. The bottom always touches 0.05 when it's done correctly. But under the alternative, I can imagine how many different scenarios. How many different scenarios could I throw out there?
Infinite.
An infinite number. That's the problem. So let's just start with this one. Let's say 30 versus 27.5. Let me ask you something. What do you think is going to be easier to spot? 30 versus 27.5 or 30 versus 25? Assuming all other things equal, use your intuition. What's easier to spot, a 2.5 difference or a 5.0 difference, assuming all other things are held constant? What's your intuition? Which one's more false? It's a trap question. Y'all aren't talkative this morning. Is it coffee? Did they give you decaf? Which one's more false? They're both. The null is false under both. One has a bigger effect compared to the other. And all other things being held constant, the bigger the hypothesized effect, the higher the statistical power will be. So it's always going to be, if you push these means further apart, then power, all other things being held constant, sample size, variance, type 1 error rate, power is going to start going up. Suppose I said under the alternative, mu1 is 30 and mu2 is 29.999. What do you expect? Is the null true? Is the null true if I put those two possibilities out there? Mu1 is equal to 30 and mu2 is equal to 29.999? No. That's a power situation. But if you want to spot that, you're going to have to drive your sample size very high, because now you're looking at something very small. Okay? So this is the way the game plays. The bigger the effect size, the smaller the overall sample size. The smaller the effect size, the bigger the. So they are inverse to each other. That's assuming all of the things are held constant. And I'm going to keep saying that word, assuming. Okay? But this is the way I want you to imagine things. Okay? Literally, if you can walk out of here and keep this image in your head, or better yet, I can send you the slides. You can keep this in your head. This is power. This is what Neyman Pearson was trying to show, and keep it simple. Okay? The top distribution is the null. Okay? That's what's going on if we assume HO is correct. That's the shape of the bell that you would expect under mathematical theory. The two green lines, the fences I've dropped, are slightly off. Well, actually, it's not slightly off because I did a t-test. So, okay, but if you would go to these tails outside the green fences for the graph that is at the top, if you could shade, if I had a magic marker and I went to Brian's really nice TD screen and shaded it, there would be 0.05 in those tails. There's literally 5% probability. Okay? But the bottom graph is what you are now assuming by what you've put down for the alternative. And by changing the means, what you've done is you've shifted. You've moved the center of that bell. And all that matters now is how much of the lower graph is falling above the green line. How much of, and how much, and even though I don't show it, there is a little bitty probability down here in the lower tail. But if I shaded this, if all I did was shade this, that's power. That's what statistical power is. It's the proportion of the curve that is falling into the rejection region when I shifted my assumptions. That's all, or I defined my assumptions for the alternative. So all I have to do is, I do the very basic thing. Let's talk about it. We're going to have to assume a standard deviation. So let's just assume a common standard deviation of 5. Also, let's assume that we're going to do a standard type 1 error of 0.05. So if the null hypothesis is true, 5% chance, then I'm going to accidentally declare, yep, we found it when nothing was there. finally assume that the researcher believes that most the budget can afford is 30, because that's the way it really goes down a lot of times. Like, people come to me and don't say, hey, what's the sample size I need? They come to me and say, this is what I can afford. What is detectable if we try to do this, and is that reasonable? Okay. So under these assumptions, I got it, but keep in mind, all right, numerous power calculators and software exist. If it is freeware, I didn't finish my sentence. Be careful. I told you I was typing at 5 a.m. Be careful and check with a methodologist. Just have somebody double check it. But all you got to do is enter the information. The difference in means that we assumed under the alternative was 2.5. I said 30 and 27.5. I give you the standard deviation, 5. Alpha, 0.05. Tell it N1 equal to N2. The software will get you power. They'll calculate it out and tell you what is the area here in the lower graph. And the area in that lower graph is, or instead of saying area like a statistician would, 48%. Okay? The amount of probability sitting inside the green beyond the bars for the lower graph. There's 0.48, pretty much 0.4779. That's the amount of probability that is beyond the green line. Okay? Keep in mind that for all the bell shapes, all of it, if you shaded all of it, it goes to 1. So you've got about 48% power here. You got about the chance of flipping a coin. Yes?
Is that a dumb question? So does
No,
that
there are
mean
no dumb questions.
If you're testing like a one-tail versus two-tail,
Mhm. So if I did a one-tailed versus a two-tailed, that's a great question. Let's go here. What's going to happen is you're going to lose the low. Let's say we're doing an upper tail test that we want to go greater than. Okay, it's got to be greater than, not two-tailed, but greater than. You would lose the lower green bar. It would not appear. And the upper green bar would slightly move back toward the center. So it would not have to be forced so far out. Now what that would do, naturally, is typically, if the assumptions are allowed to be correct, you're going to get a little bit more power, or you may be able to get away with a little bit less sample size. But typically, I'm going to tell you this, I've never had a one-tailed test successfully reviewed in a grant application. Even if I can make all the arguments in the world that if we are going to have an effect, it's going to go in this direction. For some reason, it's ingrained that it needs to be two-tailed. And when I backed up and made it a two-tailed, it's gone through. Okay? So, but that was a very good question. It does matter the number of tails, and you need to, in your write-up, indicate the number of tails that you're discussing. Okay? Now, this is a classic thing. Notice, and I do want you to listen to this, because one of the things that drives me insane in study section, again, your power calculation can be absolutely correct, and I'll triage. Why? Because you do not give me the sufficient information to replicate it. I can tell you when an epidemiologist or methodologist or statistician who's done a lot of grant applications has written the power calculation, and I can tell you when the clinician has written the power calculation. I can very much split the difference. I do not make that mistake. And I also know when people are playing the BS card on their power calculation. Okay, because key pieces are missing. Okay? Key pieces that any statistician would say, I can't report this without telling you this, will be missing. So assuming a two-tailed hypothesis using a type 1 error rate of 0.05, I've already laid it down. There's one of the assumptions. Two tails, I'm going to live with a type 1 error rate of 0.05. You cannot report your power calculation without talking about what is your type 1 error rate. And a common standard deviation of 5. You usually have the standard deviation. If you can't tell me how variable the data is, or you're not willing to assume the variability of the data, then we got a problem. It's got to be there. So you need to report out type 1 error rate, standard deviation, and then a total sample size of 60. And I am very careful to do this. I will always indicate, because people review their review grants at 2 a.m. I'm not joking. Just go on and tell them what the total size of the experiment is, and then remind them how many groups you've got. Give them as much detail as you can. Don't make them think, please. Give it as much as you can, provide, so 2 groups, we got 30 per group, provides 47.79% power, and then I go as far as to say, to detect the difference between 2 group means of 30 and 27.5. So you see, if we walk through this, you got the type 1 error rate stated with the number of tails. You've got your standard deviation, you've got your sample size, and you got your effect size, the last piece. And the piece you solved for was the 47.79. But it gives everything for somebody to come back with their software to get the exact same, confirm, yes, that's 47.79. And that, if they can do that, bonus points. They feel like you have been more thorough and you've provided the details. Okay? Moving the means increases the power. Notice I kept every assumption the same. Still 2-tailed, still 0.05, still 5, okay? But I decided to go from 30 to 26.322. And that will give me exactly 80% power, okay? Now, I put this example in here to kind of teach, to warn. What I did is I actually said to the computer, find me the difference that would map to 80%. Okay? So I actually programmed the software to say, this time I want you to, I'm going to give you 0.05, I'm going to give you 5, I'm going to tell you we're using 30. Now I want 80% power. Now computer, you tell me what's the minimum distance to put the 2 means apart. A lot of people will come to me and ask me to do this, and I will do it, and then I will dig my heels in and fight like a dog. Because they're going to say, okay, that's the one I'm going with. No. You just declared you'll say anything that has 80% power is clinically relevant. That's not right. More important to focus on the clinical relevance. Okay? All right. I can also play this other game. Change the program again. Came in and said, assuming a 2-tailed hypothesis using error rate of 0.05, common standard deviation. This time you tell me the sample size. Give me the sample size this time that will give me 80% power for this difference I'm really interested in, the 30 and the 27.5. So this time I changed the order that the information went in and said, now solve for this unknown. So it came back and said, all right, now look, if you're really going to say, dig your heels in and say a 2.5 difference is clinically meaningful, and these are your assumptions, then if you want 80% power, go all the way up to 64 per group. Okay? But all these things, all I'm doing is, all these things are just changing how far this distribution below is being able to spread out. Okay? Because if I increase my sample size, I'm actually making it tighter. I'm bend it in. Every time I change any assumption in that power calculation, I warp this guy. I can warp it all day long. I can mold it under different assumptions. If I drive my sample size up, I make it get in much tighter so that more and more area is falling above. If I change my assumption of my standard deviation and I decrease it, I again make it tighter. So more power, okay? If I raise my alpha, don't do it. If I raised my alpha, I'm going to get more power. There's many levers, but you don't want to just, I've seen plenty of power calculations that come in where clearly they chose the most optimistic situations to keep the sample size as small as they could, and it's just not reasonable. Yes?
Could you speak to the implications? So say rather than the 30 and 27.5, you have reason to believe that it's 50 and 47.5. So the same 2.5
Great
difference
question.
but you have a difference in what your kind of expectation and alternative hypothesis are.
So let me say this, all right? Here's the great thing. No, let's go back to this. That's a great question. Right here. I'll do this power calculation off the top of my head. He said 50 and 47.5. Okay, off the top of my head. Assuming a two-tailed hypothesis using a type 1 error rate of 0.05 and common standard deviation of 5 and a total sample size of 128, which is 64 per group, provides 8% power to detect the difference between two groups, means of 50 and 47.5. Scale is location invariant, is what, that's the jargon they taught me in graduate school. It's location invariant. It's the difference that matters, not where the means are per se. It's the difference that really, really matters. Okay, so it's not so much the 30 and the 27.5. It's because the 30 and the 27.5 maps to a difference of 2.5. Guess what? 102.5 and 100. I still got 2.5. It's still going to be the exact same power calculation. And when we program it in either SAS or in we have, one of the most expensive software the department purchases per year is PASS, which is power and sample size. We use that fact to our advantage all the time with regard to building power calculations, that it is location invariant. But here's the catch. This is why you meet with a statistician. Now we're going to go to proportions. I love it when people come and ask me to do proportion power calculations. I love it because it's so much easier to get the information. But y'all hate me because it's much more expensive. It's much more problematic to get the sample size because power sample size just runs right through the roof. Okay? I don't start showing graphs again because it's the same story. It's really very much the same story. But the reason I like doing proportions, it just means that you got yes, no. I've got treatment 1 and I've got treatment 2. I want to know the proportion that resolved their migraine within 4 hours on treatment A, and I want the proportion that resolved their migraine on treatment B within 4 hours. Yeah, did you beat the clock? Yes or no? That's all it is. Power calculations for me are much easier when they're proportions because all you got to do is give me the proportions. You don't have to worry about coming back and saying to me, what's the variance? Statistical theory already tells me what the variance is. I don't need I can just go back to first principles. I know what the variance has to be. That's the truth. Effect size is already there because you give me the 2 proportions. So everything I need, except for the type 1, is there. So it's very easy. So the proportions takes everything I need, so you don't have to worry about standard deviations. That's why a lot of statisticians want things to go to a dichotomous outcome. However, it runs your power or your sample size up. So statisticians always go to different symbols when we go to proportions. So if we're talking about the pi 1 and pi 2, let's just say 20% response rates in both groups, so the null is true. Okay. Now if we go to imagine a scenario that's not true. So we're talking about pi 1 is equal to 0.2 and pi 2 is 0.30. So that, there is a relative risk of 1.5 if you want to talk about it that way. You want 80% power. Congratulations, I need you to give me a total sample size of 588. So it gets much more problematic. Okay. The other thing, and that's a two-tailed test, a type 1 error rate with a two-tailed test. The other thing that you have to keep in mind for proportions, the difference is not scale invariant now. If I took this to be 0.5 versus 0.4, you don't want to see that number. Because anytime, especially when you're designing experiments, if one of your groups moves towards 0.5, a 50-50 chance, you have maximized your variability, and therefore it becomes, and as variance goes up, you got to have a higher sample size to deal with it. So be careful. Remember, proportions, unlike continuous outcomes, It's not invariant. What you assume alters everything. So at this point, if Muggs came back to me and said, okay, now do 0.4 and 0.5, I can't do that. I got a calculator right here, but I can't do it off the top of my head.
I think this is such a critical point in terms of where you get these estimates from and how important they are, and to emphasize this, but the idea of seeing a lot of big multi-million-dollar trials fail despite adequate power because they were off in terms of what their anticipated effect size was, be it as a proportion. So, the really being very thoughtful, as David has said, about what you expect, grounding that in literature, and having as best of an estimate as possible that is driven by published data and expectations, not by, oh, I'm going for 80 and 70, I need a smaller sample, but if that's not what the literature is telling you is, without intervention, the effect size, you can really kind of derail your efforts.
You can cut yourself off at the knees really, really quick. But to go back to Muggs' point, it's very interesting to collaborate with so many different groups across the campus. Some groups will want me to say, just write the paragraph, David, let's go with the assumptions. There are other groups who, and I actually have over the years become much more a fan of this. Even if what you find is in literature is what you believe, it's still an estimate. It's an estimate. You go and you try to recreate exactly that. Okay, can you step in the same river twice? Technically, no. The river is moving. So certain things are going to change. So build the grid instead. And this is what I put in almost every grid. I'll say, let's assume on the rows to be the variance. Let's assume the columns to be your desired effect size, or the difference between your means. And what I'll do is I'll come in and say, okay, let's do this table grid or this power grid. So if you are looking at 2.5 and 2.5 as the assumptions, and we are holding off with a specific sample size of, I believe at that point that is, yeah, this is where we're still doing the 30 and the 30. Then under that set of assumptions, you would have 97% power. However, as the difference in means increases, what's happening as you look at any given row? Look at any given row and read left to right. What are you seeing? As the effect size grows or the difference between means grows, what is consistently happening with my power? It's going to increase. What happens as you move and your data becomes noisier? What happens if you condition on a column and read going down? What's happening? As the data is noisier, what's happening to your power? Down. So this lays it out, and under this scenario, you can pretty much, a study group would recognize, hey, an effect size of 2.5, they're not in safe territory. However, if they are starting to move up to 3.5 or 4.5, they are moving, if that's what they're hypothesizing, that is much safer. And what I'll do is I'll build a grid and show, look, this is the region we're trying to avoid, and almost all of what we are setting up and believing is sitting up here in a safer region. Okay? ANOVA. What is ANOVA? Anybody? Oh, I heard it. Analysis of variance. I don't know what that means. What does it mean to be analysis of variance? It's the great riddle.
Are the means of two or more groups different from each other? Doesn't tell you how they're different, but are there differences?
But you already said it perfectly. Analysis of variance is not a hypothesis about variances. It's a hypothesis about means. Analysis of variance comes about when you're asking, can I do a test of technically two or more means? We usually default to it when we get to comparing three groups. So when we have continuous outcomes for multiple groups, okay, I could transform any two sample t-test I want to into an ANOVA, but that's using a battleship to kill a fly, okay? So what I'm doing here is I've got more, and I want to compare the means. I'm going to have mu1, mu2, mu3. The null hypothesis, I'm going to play here with three groups, that all the three distributions now all line up on top of each other. And then I want to start imagining scenarios where they don't line up. Only one problem. There's a lot of permutations for that. There are going to be a lot of them. The alternative is that I just have to take one mean, at least one mean, and move it somewhere. Okay, so this one gets a little bit more complicated. If it's a test of means, why do statisticians aggravate people by calling it analysis of variance? Basic. If mu1 is equal to mu2 equal to mu3, there is no variance among those three numbers. There's no variance among the parameters that define the center. They're all constant. So analysis of variance is zero. There's zero variance there. Under the alternative, when mu1, mu2, mu3 do not equal each other, I can see variance among those parameters. Okay, and that variance contributes to the variance of the data. So here we go. Guess what? I've already taught you every principle about power. You got to write your null down, and then you got to start imagining scenarios where there's what's a possible scenario I would like to investigate under the alternative. So mu1 is equal to 30, mu2 is equal to 25, mu3 is 20. I just picked them out. I made it a staircase. Move them out. Okay? Note that the combinations I threw out for the alternative is just simply one of an infinite number of possibilities. And trust me, you're not going to report all of them. We could assume other possibilities. We could assume 30, 25, 25. That's another possibility. We could assume 30, 30, 25. How are you going to know? Not from the statistician. You're going to have, based upon your understanding of the literature, based upon what you are designing, based on your clinical opinion. But I had to show you a graph, okay? Because every power calculation shows two distributions, one for the null, one for the alternative, and what's true. As I change my assumptions, what's going to happen under the alternative? It's going to do what? It's going to warp. It's going to shift. It's going to move left. Under the ANOVA calculation, it will literally move like a wave. It's like a wave being shoved forward. And you will see more and more of the green, which is under the alternative, being pushed above my critical value or my cut point that defines my rejection region. Because under the red, going up to the upper tail, going toward, if I'm facing it my right, there's 5% of that little bitty area, 5% of that curve is falling above that cut point. So the game is my assumptions will actually warp and change the shape of the green, okay? And I just mapped out one of the possibilities. But it's the same game. So where's power? And let's answer this question. Where is power on that graph? If you were going to shade something, what is the power of your hypothesis test?
Between the green and the red line to the right of the blue line, right?
So it's all of the area for the green curve that is falling above 3.14. It's all of it. That's what is the power. And if you can alter that shape with assumptions and push more and more of it above that line's not going to move. That one is defined for the null hypothesis. So the assumptions change the shape of that. Okay? Now, here's a question for you. Why aren't there 2 bars? That's a two-tailed test. Why aren't there 2 bars? I wish I had the Jeopardy theme.
That's like a probability distribution. It's like
So is the two sample t-test, and I gave you 2 bars there.
but like as you approach 0, you approach 1 in terms of probability. So you can't go. You can't go past 100% probability. So like on that graph.
So let me ask you this, all right? So here's the thing about, it's an analysis of variance, okay? It's technically an analysis of variance. So literally when I summarize all my data and all my evidence, I'm squaring it. I'm squaring it. And because I'm squaring everything over and over, everything is being thrown to the upper tail. All evidence must be thrown to the upper tail. So even though that technically this is a two-tailed test by the alternative, because of the mathematics of it, you only study. And this is why you meet with statisticians. You only, because you would never write for a two-tailed test here. You will just simply say for a type 1 error rate of 0.05. If you put that in there, then you know the statistician, either the statistician was not thinking, or a statistician or a methodologist didn't write it. Okay, so let's do one really quick. Assume that the common standard deviation is 15. I also assume we wish to use an alpha of 0.05. Notice I did not say two-tailed. I just said an alpha. Finally, assume that the researcher believes that at most the budget can afford 30 per group. This person is really stuck on 30. Okay? And this is the way I'd write it out. Now this gets much, notice what I'm doing here. This one got much longer, didn't it? Because I came back in and I said, all right, under those assumptions, then we get 61.6% power to detect the difference among hypothesized means of 30, 25, and 30. 30, 25, and 20, using an F-test with a 0.05 significance level. The size of the variation in the means is represented by the standard deviation, which is 4.08. In other words, I've come back so that they can work out, that have everything that they see. I told you that there has to be some variance or standard deviation among the means. I've reported it. This will help people. All this information will allow multiple people to come from multiple angles to get right back to that number of 61.6. But I'm going to tell you this right now. You leave out that assumption of 30, 25, and 20, and I'm just guessing. I'm guessing. Okay? Now, I could backtrack it. I could still get the 61.6 by these 2 pieces of information. But the more details you can give, you may think, honestly, oh, I just don't want to show it all. I'm going to play it safe and not show all my cards. Wrong strategy. Show all your cards. Put it out there. Everybody who's in that room knows it's a clinical opinion. Okay? Usually they don't stop me for saying, I don't believe your assumptions. What they usually stop me for is, I can't replicate it. Why can't I replicate it? So, all right, and here's the other game that I've done. Now, I want somebody to study that graph for me and tell me, is there a typo? Because I really do work a lot between 2 and 6 a.m. Did I make a mistake? I make mistakes multiple times a day. A mistake in that table? What does anybody notice? Brian, what do you notice?
I don't know, say Tulane.
Tulane, what do you see? Tulane, are you there? Reminds me of a really, that's a rabbit trail. I'll go there. If you want to know that story, I'll tell you that story later. It's a very interesting book about a hurricane in 1901. Telegraph's going, Galveston, are you there? And nobody responding. No, we heard something. All right. All right, that's no problem. What do you see? What do you see in the table? Do you think I made a mistake? What do you notice about rows 2 and 3? The numbers are identical. Reading left to right. Did he copy and paste and make a mistake? Who all votes Dave did not have enough coffee? Who thinks David did not make a mistake? Why? It's not a mistake. I'm trying to illustrate a point.
You're looking at the variance in the first one, there's a variance between each three, so there's.
So this is a unique variance among mu1, mu2, mu3 being 30, 25, and 20 creates a specific variance for that set of means. However, the variance is technically the same for these two groups. For these two categories, for rows 2 and 3, though the means are different, they're mapping to the same variability. Therefore, they're going to have to produce the same power. So not every combination goes to a unique situation. Now, I know you're saying, David, that's going to be a lot of work for us to hypothesize these. That's what we're here for, to help you strategize how to build these things. Again, I don't have an ounce of training, clinical training. I mean, I've learned all of the biology I know from sitting around collaborating with people. I don't expect you to know all the theory of statistics. I don't expect you to be able to work all of these things. And even if you did, I bet you 10 to 1 I can do the power calculation faster than you can. And so why not take advantage of it? And anyway, team science is better than Lone Ranger science all day long. Trust me. Okay, so let's work with those. Now, the other thing is, notice I decreased the standard deviation this time going left to right, which makes sense as the residual variance, as we would call it in this scenario, is going down. It's less noisy. Because it's less noisy, power should be increasing. And the other thing is, if you're going to give them a table, interpret the table for them. Don't let them don't leave it without an explanation. All right? I can always come back and do the exact same thing with regard to asking for a specific sample size. If I wanted to go to the first one that had 80% power, I would need 45. If I kept my means the same, I would need 45 per group to get over the 80% range. Again, notice the only thing that's changed here is I've kept everything constant with the alpha, the variance or the spread of the means, the common standard deviation or the residual variability, kept the effect size the same, and just said change the power, change the sample size until we get to 80% or greater than 80% power. What about more complex designs, David? What about regression? Guess what? You go and you build me a regression. Sorry to back up. It's that exact same graph. It's going to be the same thing, but the assumptions, as you change your assumptions in the regression, you're setting up a different green curve, and it's going to warp and move. But ANOVA and regression both map to F distributions, and will stay there. What about things such as, I want to complicate it. Suppose I wanted to do 2x2s. What if I wanted to do 2x3s? Suppose I've done these studies where we've had 3 drugs that we randomized people to, and well, we had placebo, drug 1, drug 2. The other arm was they were also being randomized to either intervention or no intervention, so we wanted to see if there was a synergy or an interaction between them. Well, just keep in mind this, you play that game. If it's a 2x3, immediately the statistician goes 2x3. The reason we call it a 2x3 is because we're multiplying that to get to 6. It's literally why we call it a 2x3. We're not counting the dimensions on the table. We're just keeping up with how many means you have to hypothesize. Literally, the more complicated the design, the more assumptions you're going to make. So if we came together to do this, you would have to end up giving me a hypothesis or a value for each of those 6 cells. Because what you're literally hypothesizing is now I'm playing with 6 distributions. The other thing that's very interesting about this design is there are 3 power calculations to be done. I've got to know, is there a difference here? I've got to know, is there a variability based upon rows? That would help me know if there's a difference between A and B. Is there variability across the columns? That would tell me if treatment 1 is altering anything. And then I've got to start asking, is the gap here between UA1 and UB1 equal to the gap between UA2 and UB2? Is that also equal to the gap between UA3 and UB3? That's the test of interaction. When you start hearing when statisticians confuse you of, well, I'm testing for interaction. Do these two treatments interact with each other? Well, we know what that means medically, but statistically, if there's no interaction, this gap equals that gap equals the last gap. They're constant. There's no variance there. But if the gap is changing, depending upon what column you're in, that's the definition of statistical interaction. Okay? I know that's a lot, but this is my last slide. I'll give you some time back. Always have somebody look at it. Even after all these years, I will still have other people look at what I've written up on a power calculation, mainly because to make certain, do they believe the assumptions and do they believe they can replicate it, okay? If any detail is left out of the write-up, such as accidentally leaving out the type 1 error rate, I've seen it, you're going to get questioned. Big thing is a lot of times people will not even come anywhere close to defining an effect size. If you can't tell me how far the two things differ, just don't ever try to fly one by that says, well, with this sample size, we've got 80% power, period. You will be amazed how many times that statement is made, and it's a complete bluff, and it's not accepted. Always make sure somebody can replicate it. And with that, I'll take your questions. Yes?
Back to the 3-group ANOVA, can you speak to the appropriateness of doing pairwise tests if your overall p-value is not significant?
If it's not significant, as an overall test that you begin with the F, and if it's not statistically significant, then there is no evidence against the null hypothesis. In other words, you would have to say there is not sufficient evidence to reject the belief that mu1 is equal to mu2 is equal to mu3. And because you don't have that evidence, it's pretty much illogical to say, now I'm going to step down and start doing pairs, because you're examining pairs, which is the omnibus test already said there's not sufficient. Now, the problem, I'll be very blunt, what we always teach is not what we always do. Yeah, I just said it. We are very dogmatic in the textbooks with regard to if you reject and you do pairwise comparisons, then you must adjust your alpha levels for multiple comparisons. Well, one of the reasons all the work in statistical genetics and everything has been so problematic is you drive your alpha rate so low so quickly that you become underpowered greatly, on the follow-up test. So one area of research that has received a lot of interest in the past 20 years is, if I'm going to have to do post-hoc comparisons, I want to start coming in, breaking down my 3 and looking at the different combinations. How do I maintain the power? That's where the concepts of false discovery rate, where Benjamin Hochberg, as well as von Braun, Holmes, von Braun and Holmes, all of that has come into play, trying to protect power. I still struggle with it. I always struggle with it. What I'll do if I'm recording a post-hoc comparison, I'll say, this is what we get under von Braun, this is what we get under FDR, this is what we get under von Braun. Yeah.
So, a lot of us are doing secondary analysis of existing data. I think a lot of student projects and training projects. So, where you're not necessarily prospectively doing a trial and defining hypotheses. So, just any guidance from you in terms of if we are doing secondary analyses of existing data and designing those studies, your thoughts about sample size, power calculations, and how you advise us to approach them.
Okay, that is a great question. because a lot of, we go on for hours on this one, because a lot of people will say, that's a secondary data analysis, I don't have to design it. You think I agree with that? No, I don't agree with that. You bring me any data set, and I can, from first principles, take that information and still say, just based on what's going on and under certain assumptions, prior to analyzing the data, you're only going to have power to detect the following things. Is this in your clinically relevant effect size or not? Because the bottom line is, we point out to you, you could bring me a data set, I can look at it and say, based on my study of that, it's a two-group comparison. Based upon what I'm seeing, you're going to have to say, hey, I want to tell you up front, you're going to need to have a difference between means of at least 5 or greater to get to 80% power. Well, David, I was hoping it was 2.5. You're underpowered. So when you go and you say, I don't find evidence of the effect, what you're possibly doing is you're just going with an underpowered study. Now, one of the things that's a pet peeve of mine, and I'm serious about this, and I can't help you. I have one researcher on this campus that every single time is a null result. We fail to reject the null. The declaration was, oh, it was an underpowered study. No! It may very well be that there was no effect. So you have to be very careful in that approach. What you should, this is why, again, don't get married to p-values and don't get married to power calculation. Use the whole arsenal when you're studying anything. I want to see the graphs. Graphs will convince me. I want to see the confidence intervals. Confidence interval will tell me just really, literally, how precise it is, how much variability is there, how noisy is this. So it's again, it's a whole, use the whole tool set. Yes?
Yeah, no, I think that's great advice. And just thinking about, the principles you applied really seem like they should apply and could apply to secondary analyses where a lot of times you're kind of, you're about to go on a fishing expedition and you just find something. So if you, a priori up front, sit down, define your outcome variable, define your independent variable, meeting effect size, and go through these steps, and you can write that in your methods section. To me, reviewing secondary analyses is a very different lens than we looked at every variable known to man in this data set. This was 0.05, so I think that...
I think again, I will strongly encourage you in this. If you are doing a secondary data analysis, you've inherited a data set, if you're going, it's fine, I do a ton of secondary data analyses. But write down the don't do anything any different than if you were doing the design of the grant. Write down your hypotheses. Write down the analysis plan. Write down what you think a meaningful effect size is. Then come in and try to say, what are reasonable effect sizes that you can detect here? Recognizing your scenario. Then proceed to analyze the data, but don't just get hung up on your p-value. Come in, look at your confidence intervals, look at your associations, but follow that analysis plan. And that would be my, and I'll be the first to confess that there are plenty of times I don't follow my own advice, but it always comes back to bite me in the butt. Okay? All right. No, I heard something.
We're having trouble hearing you, Rachel. It's getting better.
Well, your face.
Yeah, go ahead.
Sorry, I need to get further. Is that better?
That's better.
Okay, that's better. I'm sorry. There's only a certain distance I can be. So I really enjoyed the presentation. This is such a critical issue in clinical research that we get the power calculations right. And I think this aligns with what the NIH has been talking about about making sure that we can replicate studies. Too many of them cannot be replicated, and many of them might be. Did you talk with the group, because I came a little bit late from another meeting, did you talk with the group about how you get the estimates of effect sizes that they could plug into this? I know that you mentioned something about the literature, but did you go over some of those strategies? Because I think too many times our clinician investigators aren't thinking along those lines about where to get the effect sizes if they haven't conducted the study yet.
So we did discuss it, but I think it's worthwhile to go back over it and discuss it in multiple ways. First, we always go to the literature, but we also, if you're uncertain, you can meet with fellow clinicians, and I've done this plenty of times. It's actually very good meetings where we sit around the room and discuss what is clinically relevant. And the key thing is again, realize that is an assumption that when you're doing a power calculation or you're working with a methodologist to get that power calculation, it's okay to say, would you present scenarios when we're looking at an effect size of, or a difference between means of 2.0? How about then adjusting it to 2.5? How about then adjusting it to 3.0? Because I won't walk into the room without showing all of those, because that leads to the most informed decision. And in fact, I'll present that all in the grant application. And I will also sometimes put it in the supplemental information within a manuscript to illustrate that we examined all of these scenarios, and this is the region in which we had the best statistical power. Does that answer the question?
Yeah, that's very helpful. And the only other thing I might add is, and you probably mentioned it earlier, is you can conduct your own pilot studies, right? And generate some data that way on which you can base a power calculation and design your larger study. Critical steps, it seems like a small thing, but this is one of the most comprehensive and most focused presentations on power, and it's so important in clinical research in particular. So thank you.
Well, thank you.
Questions if you all have? Oh, we have their attention? All right, no other questions on our end at this point.
Okay.
Thanks, Todd.
All right. Thanks. Next week we've got Anthony Hood coming to talk about team science. It'll be a good presentation if you haven't had a talk by Anthony. He does a good job of engaging with that. And then the week after we have Monica Baskin talking about engaging community stakeholders. So look forward to that. If there's anything, let me know, but have a good rest of the day and good weekend, guys.
I know.